Hello everyone, I'm Shreyam, a CMI alumnus, and in this video we're going to look at this problem which came in CMI 2019. Now this is a very beautiful problem because even though it looks like an algebra question where you have 3 equations and 3 variables, but it's actually not. And the solution is really going to surprise you guys. So from the first equation we can say that if x square plus y square is equal to 3 square, then we can always construct a right angled triangle with side lengths x, y and 3. So let's start off by doing that. So suppose this is 3. We get our right angle triangle with side lengths x and y. Now if we look at the second equation, we can rearrange the second equation like this. This is nothing but y square minus 2yz times minus half plus z square equal to 4 square. Now this should remind you of the cosine rule. So from here you can say that there is a triangle with side lengths y, z and 4, and this angle in between theta is such that cos theta is minus half. So from here we can say that the value of theta is going to be nothing but 120 degrees, right? And if we similarly do it for the third equation, we can rearrange it to get x square minus twice of xz times minus root 3 by 2 plus z square equal to 5. So we get a triangle with side lengths x, z and 5, and the angle in between them is 150 degrees, right? So let's complete this figure, or let's redraw it again. So you'll end up with something that looks like this. So this is going to be 3, this is x, y, this is z, sorry, this is 4, this is z, and this is 5, right? Now why can I draw a figure like this? Because if you look carefully, the angle around this point is nothing but 360 degrees. So I can complete this figure. Now, one thing you should have noticed is at no point in this question were you asked to find the values of x, y and z respectively. All you had to do was find the final value of this expression. Now this is a very weird expression. We can't really relate it with any of the equations given to us. But since we use the cosine rule in this problem, it's only fair that we also think about the sine rule. So using the sine rule, I can say that the area of this first triangle is going to be half times xy, or just the standard formula for a right angle triangle. But in this triangle, the area of this triangle is going to be half times yz times root 3 by 2, right? Half the product of the sides times the sine of the angle in between them, right? And similarly for this triangle, the area is going to be half xz times half, because sine of 150 gives you half, right? Now if you add these 3 expressions, let's see what do we get. So you get half, if you take that common, you'll get xy plus yz times root 3 by 2 plus, this is going to give you xz by 2. Take this half outside again, you'll get 1 by 4 times twice xy plus yz times root 3 plus xz, and this is precisely the expression that's given to us. Now what is this total sum? This total sum is nothing but the area of the entire triangle, which is nothing but half times 3 times 4, right? So that gives you 6. So this is equal to 6. So the value of this expression should be 4 times 6. So the final answer is 24. Hope you like this problem because it had a very unique approach. It was an algebra question and we converted that to a geometry question. So let R plus denote the set of all positive real numbers. For a continuous function f from R plus to R plus, we define AR to be the area bounded by f, the x-axis x equal to 1 and x equal to R. Similarly, we define BR to be the area bounded by f, x-axis R and R square. So you have to find all continuous functions f such that AR is equal to BR for every positive real number R. So the formulas for AR and BR are the integral from 1 to R fx dx, and BR can be written as the integral from R to R square fx dx. Now if these two integrals are equal, we can say that 1 to R fx dx is equal to R to R square fx dx. Now if we differentiate both sides, we'll get that the left hand side turns out to be just f of R, whereas the right hand side is going to be f of R square times the derivative of R square, right? So that's going to be 2R f of R square minus f of R. Now sending this f of R to the other side and cancelling out the factor of 2, we basically get this functional equation that f of R needs to be equal to R times f of R square. Now this functional equation seems a little hard to solve. So what we can do is we can define a new function gx, which is just x of fx. Now since we are dealing with positive real numbers, we can multiply both sides by r. The left hand side is just going to be g of r, whereas the right hand side turns out to be g of r square. So now our functional equation looks like, for every r in r plus. Now, since r is a positive real number, we can substitute r by square root of r. So this will turn into gr equal to g of root r. And from here, by induction, we can say that g of r should be equal to g of r to the power 1 by 2n for every natural number n. Right? Now, since g is a continuous function, if you take limits as n goes to infinity on both sides, we'll get that g of r should just be equal to g of 1, which means that r times f of r is equal to f of 1. So f of x has to be some constant, which is f of 1 divided by x. This is the only solution for this question. Now, in this question, you have a definition. So it says that a natural number k is called stable if there exists k distinct natural numbers a1 to ak, each of them greater than 1, such that the sum of their reciprocals is equal to 1. Alright, so we have to figure out which k's are actually stable. So if you look at this, let's start off with the simplest natural number. If we take k equal to 1, we want some number such that 1 by a1 is equal to 1 and a1 is strictly greater than 1. So it's obviously not possible. So we can say that k equal to 1 is not a stable number, right? So 1 is not a stable number. Similarly, if we come to 2, if you want 1 by a1 plus 1 by a2 to be equal to 1, we know that the only solution for this would be a1 equal to a2 equal to 2, right? So even this is not a stable number because you want distinct natural numbers, right? So 1 and 2 are definitely not stable numbers. Now if we come to 3, we want 3 numbers such that the sum of their reciprocals is equal to 1. And we know this famous triplet. So we know 1 by 2 plus 1 by 3 plus 1 by 6 adds up to 1. Right? And the numbers are different, they're all greater than 1. So we can say that 3 is definitely a stable number, right? Now we'll try to use this idea and build upon it to claim that any natural number greater than equal to 3 is stable. So that's our claim. Is stable. So for this what we do is we'll use induction, right? Assume that some number n is stable, right? Assume that n is stable. So you have a corresponding tuple of n numbers ai greater than 1 such that summation of 1 by ai is equal to 1. Now what we'll do is we'll use a very simple trick. So for n plus 1, when you want n plus 1 numbers, what you're going to do is you just take this summation 1 by twice of ai. So this sum is nothing but half because the sum of 1 by ai is equal to 1. So this summation should be half. So just add another half to it. So you get 1. Now, if you look carefully, for 3, the triplet that we got was 2, 3, 6. So when we go from 3 to 4, our new construction would give us 2, 4, 6 and 12. So at every step, in some sense, the first number remains 2, right? So when you multiply it with 2, the numbers are all going to be greater than equal to 2, right? So there's no repetition and all these numbers are distinct. So for any n, when you go from n, which has this corresponding n tuple, to n plus 1, our corresponding tuple is going to be 2, twice a1, twice a2, all the way till twice an. So we came up with an algorithm which proves that any n is going to be a stable number as long as n is greater than equal to 3. So this was a very simple and elegant solution to this problem. So the question goes something like this. Consider all non-empty subsets of the set 1 to n, and for each such subset, we find the product of the reciprocals of each of its elements. Denote the sum of all these products as Sn. For example, if you look at the set 1 to 3, what are the possible subsets? You have the 3 singletons, then you have subsets taken 2 at a time, and then you have the entire set itself. So if you consider the product of the elements of all those subsets, your sum should look something like this. So the first part of this question, so what you actually have to prove is that Sn is 1 by n plus 1 by n times Sn minus 1. Hence or otherwise, you have to prove that Sn is actually equal to n. So this is a very simple question. So what we are going to do is, so first of all, observe that when you go from 1 to n plus 1, technically every subset of this first set is also a subset of the second set, right? Okay. So this entire sum Sn is also going to be counted when we look at n plus 1, and we have a few extra terms. Now the question is, what are the extra terms? What are the extra subsets that you are getting? See, the idea is, first of all, you have this new singleton. This is a new subset that you did not have previously, right? Now, along with any subsets of the previous sets, if I call these sets Sn and Sn plus 1, for any subset x of Sn, we can just look at x union this new element n plus 1, and this is going to be a subset of the new set, right? So basically, when we look at the product, every term is going to be multiplied by a factor of 1 by n plus 1, right? Now, if you look at the overall sum, it should look something like this. First of all, you have the pre-existing Sn, right? So you'll get Sn. So now this S represents a sum, okay? So Sn plus 1 is going to be Sn plus 1 by n plus 1 times Sn, because we can associate this element n plus 1 with all the pre-existing elements, plus you get the singleton 1 by n plus 1. So that gives you Sn times 1 plus 1 by n plus 1 plus 1 by n plus 1. Hence, by induction, we can claim that this first part is true. Now the next part is, hence or otherwise, we need to show that Sn is actually equal to n. Again, we are going to use induction for this part. So we got this recursion between Sn. So we get that Sn is 1 by n times Sn minus 1 plus 1 by n, right? So if you assume that Sn is actually equal to, or let's go with Sn minus 1. Assume that Sn minus 1 is actually equal to n minus 1. Then let's calculate the value of Sn from here. So you'll get 1. So this is basically n plus 1 divided by n times n minus 1 plus 1 by n, right? Which gives you n square minus 1 plus 1 divided by n, which is nothing but n. Hence, again by induction, we get the second part, that Sn is equal to n for every such element, okay? So as you can see, both the parts were basically just induction proofs. So the question goes something like this. Let f be a function of non-negative integers defined as follows. So what you have to prove is, if f of 0 is 0, then you have to find the value of fn for every n. The second part is, show that f of 0 cannot be equal to 1. And the third part is, for what non-negative integers k, if any, can f of 0 be equal to 2 to the power k. So let's start off with the first part. So for the first part, observe that f of 0 is 0. So using this value, if you plug the value of n as 0 in the second equation, you'll get that f of 1 is f of 0 plus 1, which just turns out to be 1. Similarly, from this, you can calculate the value of f of 2 as f of 1, which is just 1. So these are your base values. So f of 1 and f of 2 both turn out to be 1. Now using these values, we can calculate the further values of f. So observe that f of 3 is just f of 2 plus 1 from the second relation, which turns out to be 2. And f of 4 is equal to f of 2, which is just 1. Since f of 2 is 1 and f of 1 is also 1, right? So now from here, by induction, you can see that for every even number, you'll end up with f of 1 somewhere, right? And since f of 1 is 1, for every even number, you're going to end up with 1. Now the odd values are just 1 more than the values of the even numbers, so it's always going to be 2 for any odd number greater than or equal to 3. So your function can be summarized as follows. So fn is 0 if n is 0, it's 1 if n is equal to 1 or 2, and it's going to be 1 for every n greater than or equal to 4 where n is even, and it's going to be 2 for every n greater than or equal to 3 where n is odd. So this is the final value of f, given that f of 0 is 0. So that solves the first part. Now coming to the second part. The second part is, show that f of 0 cannot be equal to 1. Let's start off by assuming that f of 0 is actually 1. So if f of 0 is 1, then f of 1 turns out to be 2, right? Now f of 0 can also be written as f of 2 times 0, which is f of 0, right? Which is, this is 1, so this is the value of f1, and this value is 1. So if you look at these two equations, you can see from one equation we get that f of 1 is equal to 2, and from the second one we get that f of 1 is 1. So this gives you a contradiction, right? So from here you can say that f of 0 cannot be equal to 1. A very straightforward simple part B. Coming to the third part. So the third part is, for what non-negative integers k, if any, can f of 0 be equal to 2 to the power k. So f of 0 is 2 power k, right? So f of 0 is f of 2 times 0, which is f of 0, which is 2 to the power k, sorry, f of 2 to the power k. So from here we can say that f of 2 to the power k is actually going to be equal to 2 to the power k, right? And from here we can also say that f of 2 power k plus 1 is just going to be f of 2 power k plus 1, which is 2 power k plus 1, right? Okay, so now let's see if we can find the values of f of 1 and f of 2. So f of 1 is just going to be f of 0 plus 1, which is 2 power k plus 1, and f of 2 is f of 1, which is f of 2 to the power k plus 1, which we know is 2 power k plus 1, right? Okay, so we get these two base values. Now using f of 2, can we find the value of f of 4? Let's see. So f of 4 is f of 2, which is f of 2 power k plus 1, which is 2 power k plus 1, right? So from induction, we can say that f of 2 to the power n is equal to 2 power k plus 1 for every n in natural number. We just induct on this fact, right? But for some n has to be equal to k, right? And we know that f of 2 to the power k is 2 power k, which is an even number. But from here we are seeing that f of every power of 2 turns out to be 2k plus 1. That gives you a contradiction. So there cannot be any non-negative value of k such that f of 0 is 2 power k. So if you like this video, if you like the solution, please do let us know in the comments for further videos.